So now we'll consider the inverse of a larger matrix. In general, a matrix is invertible if and only if its row equivalent to the identity. And in this case, any sequence of row operations that reduces A to the identity also transforms the identity into the inverse. So this gives us our basic algorithm. We need to form an augmented matrix with A on one side and the identity on the other. And then we'll row reduce it to get the identity on the left side, and A inverse will pop up on the other side. So here, 1, 0, 5, 2, 1, 6, 3, 4, 0. On the right hand side, 1, 0, 0, 0, 1, 0, 0, 0, 1. The first thing we'll do is get a 0 in the first column. So the first row will be left alone, and so will the second for now. So we'll do this by doing -5 row 1 plus row 3. So -5 plus 5 is 0. -10 plus 6 is -4. -15 plus 0 is -15. And -5 plus 0 is -5. 0 plus 0 is 0, and 0 plus 1 is 1. Continuing this process, we have a 1 in the second row, second column. So we'll work to get zeros in the rest of the second column. So we will do this starting by doing -2 row 2 plus row 1. 0 plus 1 is 0, -2 plus 2 is 0, -8 plus 3 will be -5, 0 plus 1 is 0, -2 plus 0 is -2, and 0 plus 0 is 0. To do the next one, we'll do 4 row 2 plus row 3. 0 plus 0 is 0, 4 minus 4 is 0, 16 minus 15 is 1, 0 minus 5 is -5, 4 plus 0 is 4, and 0 plus 1 is 1. We now have a 1 in the third row, third column. So now we work to get the zeros in the rest of that column. So my third row is completely set. I'll now do 5 row 3 plus row 1. 0 plus 1 is 1, 0 plus 0 is 0, 5 minus 5 is 0, -25 plus 1, -21, 20 minus 2 is 18, and 5 plus 0 is 5. -4 row 3 plus row 2 will give me a -20, -20, 16 plus 1 is 17, and then 4 plus 0. So now I have the inverse. A inverse is -21, 18, 5, -20, 17, 4, -5, 4, 1. Now let's do this one. So I'll set it up the same way. I'll have my matrix on the left and the identity on the right. I already have a 1 in the first row, first column. So let's get zeros underneath it. Minus 2, row 1 plus row 2. So that's negative 2 plus 2 is 0. Minus 14 plus 3 is minus 11. 6 plus 1 is 7. Minus 2 plus 0 is 0. And then I have a 1 and a 0. Negative 2 row 1 plus row 3 gives me a 0. Minus 14 minus 8 will be minus 22. 6 plus 8 is 14. Minus 2 plus 0 is minus 2. And then 0 and 1. Normally, we would work to get a 0 or a 1 in the second row, second column. But I'm going to put that off for just a minute. Mainly because that will introduce fractions, and I'm not quite ready to do that yet. In particular, when I can do another operation first, which will be negative 2 times the second row plus the third. So that'll be 0. I then have 22 minus 22 is 0. Minus 14 plus 14 is 0. 4 minus 2 is 2. And then minus 2, 1. So we'll see this row of zeros right here on the left, which means it's impossible to convert this to the identity matrix. So this particular matrix is not invertible. So anytime you're row reducing and you get this row of zeros, that will indicate that the matrix is not invertible. So a few properties of the inverse. So the first one, if A is invertible, then A inverse is invertible, and A inverse inverse is equal to A. So I'm going to prove that one. Let's assume that A inverse has an inverse. Let's call it C. So I'm going to let C be equal to the inverse of the inverse. Well, then by properties of the inverse, I know that C times A inverse is equal to the identity. But I also know that A times A inverse is equal to the identity. And since the identity is unique, C has to be equal to A. So that gives us the first one. The second one, if A and B are invertible, so is the product AB, and AB inverse is equal to B inverse A inverse. So in this case, I want to show that this is the inverse, so I'm just going to take AB and multiply it by what I'm claiming to be the inverse, and see what happens. So parentheses really don't matter here. I can move them around as much as I want. B inverse is going to be equal to the identity. Multiplication by the identity really doesn't change anything. So now I just have A inverse, which is equal to the identity. So I have shown that these are inverses by just multiplying them and getting the identity. My third one is to show that A transpose inverse is equal to the inverse is equal to A inverse transpose. So basically saying when you want to take the inverse of the transpose, you can do that, or you can take the transpose of the inverse. It doesn't matter which one you do first. So I'm going to ask you to do this one. However, I will give you a hint. It's going to be similar to the last one. Let's multiply A transpose times A inverse transpose to show that this is the inverse. And I'm also going to tell you to use properties of the transpose. So properties of AT. So there's your hint.